Now we'll review some basic theory for functions. What are they, and how do I check if a mathematical description I have is a function? Okay, so the simplest way to think of functions is that they send an input to a unique output. Okay, so functions are basically a way of quantifying certain types of relationships. Okay? Now, it's important to understand that from a mathematical standpoint, functions are very broad. They don't have to just be things like assigning one number to another number. Right? They are often, but not always, numerical. They can act on a variety of different types of objects. You can have functions like, for example, on words. A function on a word could be something like, tell me how many times the letter E appears in the word. So the input's not a number, but the output is. Okay, so really, the idea of a function is very broad and flexible, which is why mathematicians like it. It's useful for many different scenarios. So what's the notation? Well, I've already been using it a little bit implicitly. The classical notation is that f of x denotes the output of a function f at input value x. So the letter f is sort of a way of saying, this is the rule. This is how to take the input and get the output. And then the variable x is a way of denoting what the input looks like. So for example, a very standard something would be like f of x equals x squared plus 7. This says when I input the number 1, output for me the number 8. When I input the number 2, output for me the number, I guess it would be 11. So it's a way of codifying this relationship. Okay? In general, it's nice to have an explicit formula for the function, a very precise rule that says, given this input, get this output. Though it is possible, especially in higher mathematics, to have no explicit formula, to instead have what's called an implicit formula, but that's not something we're going to cover. Okay? Now, the language of function theory is somewhat abstract, but that lets it be very universal. So, almost everyone in quantitative fields uses the notion of functions. I mean, not just mathematicians and physicists, but engineers, computer scientists, economists, psychologists. It's just a very universal language. Okay? So an important question is, given a geometric or pictorial representation of a relationship, does that define a function or not? And the question is, do I assign a unique output? Is each input assigned a unique output? Or is it possible to input one thing and get multiple outputs? If you get multiple outputs, it's not a function. You need to have unique inputs. So here, let's think about inputting things on the x-axis and outputting things on the y-axis. And we ask, is each input given a unique output? So I take an input 0, it gets a unique output of 0. I take the number, I guess the output's minus 1. Take the input 1, get the unique output 0. Take the input 1.5, get the output something like 1.4. So it looks like yes. Each input gets a unique output. Let's look at this other example that I have side by side. Here, if I think of having the input x equals 0, well, I get two outputs. I get the output y equals minus 1 and also the output y equals 1. So one input got two outputs. Bad. Not a function. Okay, so no. Inputs here can have multiple, in particular 2 outputs. So this means it's not a function. Right, now what did I really do here? I basically checked for a value of x whether there were more than one possible y value. Now there's a way of codifying this and saying what I need to do is take vertical lines and intersect it with the plot of my purported function. If each vertical line intersects the function at most once, then it's a function. Because this said, well, there was at most one output value for that input. If it hits it in multiple places, well, that means for that vertical line, at that x value, I have multiple outputs, which means I cannot be a function. So this gives me the idea of what's called the vertical line test, or VLT. So it's just a trick, a simple way to do it, for checking if a mathematical relationship, when it's plotted in the Cartesian plane, is a function or not. So what I do is I draw some vertical lines, like say this one here, and this one here. And if every vertical line hits the function in only one place, if every vertical line hits the graph in only one place, then you're a function. If there's any place in which it hits the plot 2 times or more, not a function. So here we see the circle clearly fails the vertical line test, whereas this plot of y equals x squared plus 1 passes. Okay, so let's take a look at a function and a graph and try to decide using the vertical line test if it's a function or not. Okay, so y equals x squared plus 4. This is one of those types of functions you maybe want to kind of start to get in your memory. They're very common on the CLEP exam, but we can always just plot individual points and try and find the pattern. So let's do that, x and y. If x equals 0, y is 4. Get this. So this is my picture. Y-axis, x-axis. And I ask, does it pass the vertical line test? Well, every vertical line's hitting it in only one place, so this passes the vertical line test, and it implies it's a function. Let's look at a different plot. All I've done is switch the roles of x and y. Okay, now I have x equals y squared plus 4. And we'll ask the same question. Plot it, and is it a function or not? So I'll generate my nice axes here. Y-axis, x-axis. Same game. Maybe it's more convenient to have y here. So y equals 0, I get x equals 4. So a sketch is something like this. Okay, so I have, again, this sort of bowl shape called a parabola. So this shape is called a parabola. But it opens the other way. The other one was opening up vertically. This one's opening up horizontally. So we check, does it pass the vertical line test? Well, I start drawing them, and I see many failures. Okay, so this fails the vertical line test, which implies it is not a function. Okay? And in fact, when you're being asked about the vertical line test, in many cases, you don't even have to have a formula for the function. All you have to do is look at the plot. So this is a very nice CLEP type question. They show you a bunch of different plots of potential functions, and they ask you which one is a function or which one is not a function. Okay? And you don't need the formula for them. All you need is the visualization. So let's just look at a couple. So something like this maybe. Okay, so this, if you're familiar, would be maybe like something related to a sine or a cosine function. Looks complicated. It's kind of repeating itself somehow. But for us, it doesn't really matter. Is it a function or not? Well, I draw some vertical lines, and each one is only intersecting the function once. So it passes the vertical line test, which implies that it's a function. And we could draw something like, some nice curve. Okay. To illustrate the point I want to make, all I need to do is see if any vertical lines hit the function more than once, And the answer in this case is yes, right? I sort of drew a curve that I knew was going to fail the vertical line test. Okay, and all I need is one vertical line to intersect multiple places to say it fails the vertical line test, so not a function. Okay, and let's look at one more. So here's something maybe we haven't seen yet. This is actually the plot for f of x equals absolute value x, which, to recall, it's equal to x for x less than or equal to, minus x for x less than or equal to 0, and x for x greater than 0. Okay? So it kind of makes this V shape that comes together in a sharp point, right? So it looks a little bit strange. Normally functions that we encounter are smoother than this. They don't have these sharp points. But if it's the question of whether it's a function or not, that doesn't matter. I'm just looking to see if it passes the vertical line test. And it does. So one more point to make about functions is sort of what they're actually used for, which is they're used typically to represent mathematical relationships. So if I have an idea of, given a certain input, my output should look a particular way, or in another way of saying it, if I have a known rule for manipulating the inputs into the outputs, I can write this as a function. Okay, so I really like this diagram here because it emphasizes the idea that functions are just inputs and outputs, under the assumption that each input gets one output. Okay, so an important idea is to sort of model with functions, to say, well, there's some physical or economic or sociological relationship I'm studying or interested in. Can I write a function that governs this relationship, either based on data that I have or an idea about how this ought to work? Okay, so a very nice sort of classical example is what's called an exponential model. Okay, so here the model is something like f of x would be like, I don't know, a to the power x, essentially. So the function that you're looking at or that you believe governs the underlying physical situation is like an exponential function. Okay, so these are very common in like basic biological scenarios where you have a population of living organisms and that population is growing in some way. Okay? Maybe you would say, well, the way that it grows is after a certain amount of time, the population size has doubled. I mean, in your mind, maybe you imagine like, the kind of videos of like cells splitting and becoming two. Well, if I wait long enough, every cell will have split into two pieces. Okay, so the population grows in this sort of doubling way. This is perfect for exponential formulas. So for example, biologists like to use fruit flies for experiments, I think, because they grow very quickly and are kind of expendable. Okay, so suppose a colony of fruit flies starts with a population of 10 and then doubles every hour. How can I write a function that tells me at a given time how many fruit flies I have? Well, at time 0, I have 10. At time 1 hour, I've doubled to 20. At time 2 hours, I've doubled to 40. At time 3 hours, I've doubled to 80. Well, you can maybe see the pattern here. I have the following formula. P of t equals 10 times 2 to the t. Right? So 10 is referring to the starting amount, and the 2t is referring to the doubling. So if I look at a visualization of this, if I plot this function in the Cartesian plane, I get this feeling that, wow, this population is growing very quickly. So I look at it. At time 0, I started with 10. At time 1, I had 20. At time 2, 40, 80, 160, and then, wow, up to 320. Right? So this sort of model where I have this very sharp growth is very indicative of the exponential model. In reality, a lot of biological situations are not this simple. Maybe if there was too many in the population, there wouldn't be enough for everyone to eat. So in reality, a lot of these real-world scenarios are not quite as simple as exponential growth. But it's a very good place to start if you're trying to model one of these things, is to say, well, maybe if there was sort of no limitation on the amount of food they had to eat, the population would double, every so often. And from that, you can go on and then create a more refined model. You can sort of add new things to it to make it more reflective of reality.